Hello, everyone. Welcome to the 2021 ACOM seminar series. Today, it's our last seminar for 2021. And it's an honor and a pleasure for me to introduce Dr. Jiajue Chai. Dr. Chai is an assistant professor of environment and society at Brown University, where he studies sources, sinks, and atmospheric processes involving reactive nitrogen species for understanding their implications for air quality and climate and health. Jiajue got his PhD in atmospheric and environmental chemistry at State University of New York in Syracuse. And he got his master's in applied chemistry at Renmin University of China in Beijing, and his bachelor's in environmental sciences at Nanjing Forestry University in Nanjing, China. Many of you might know him because he participated to the Fire Lab, FireX, and Weekend campaigns. And his research focuses on characterizing sources and sinks of atmosphere of nitrous acid, or HONO, to constrain its budget and help predict and mitigate pollution and climate change. HONO and its fate is also the topic of his talk today. But before starting, I would like to remind you that we still have a slightly different format since last time. If you're watching in streaming, you can either you can enter a question down below in the Slido window, and at the end of the presentation, I will read those questions out loud. And if you're an ACOM scientist, you can log in via Zoom, and you can raise your hand or try to catch my attention in the chat at the end of the talk if you have a question. And at the end, we'll also have a question session without recording for the ACOM scientists. And with that, I introduce you to Dr. Chai. Jiajue, please take it away.
Okay, thank you very much, Ali, for the introduction. First of all, I would like to thank John and Ali for the invitation. And it's my pleasure to give a talk at NCAR. So as Ali introduced, my current research and my biggest interest is to tracking the sources, chemical transformations, and the fates of reactive nitrogen in the atmosphere and track their influence on the air quality, climate, and human health. And so today, I would like to talk about my recent focus, which is probing the fate of atmospheric nitrous acid via stable isotopes. So before I start my talk, I would like to give you an outline of what I'm going to talk about today. So first of all, I will give a brief overview of the reactive nitrogen chemistry in the atmosphere, and then I'll talk about why I'm very concerned about reactive nitrogen, and I'm interested in nitrous acid and their impacts on atmospheric oxidation dicing capacity. And then I'll introduce the tools that I use to constrain the HONO sources, chemical processes, and sinks in both lab and the field, which is stable isotopes, and talk about how the stable isotopes can complement the concentration measurement. And then I will discuss the deployment of the new method in different platforms, in different field field campaign to track different sources. And last but not least, I will talk about the ongoing and future work. Okay, first, this is one of my favorite figure. That's from Hewitt and Crow in 2020. That shows the basic process of the atmospheric chemistry. So basically, organic molecules emitted from both natural and anthropogenic sources, once they enter into the atmosphere, they undergo atmospheric oxidation processes and form secondary products, including ozone, CO2, and organic particulate matter. During the process, reactive nitrogen plays a very important role, both directly emitted from the sources and secondary formed via the reactive nitrogen cycling. Reactive nitrogen play an important role in determining the atmospheric oxidizing capacity. For example, HONO is major hydroxy radical source, which determines the lifetime of many trace gases. And during the organic molecule oxidation process, NOx plays very important role in determining the branching ratio of the oxidation, as well as the secondary formation of ozone. And the oxidation of reactive nitrogen will lead to the formation of nitric acid, which behave as nuclei condensation nuclei, which determining and affect the particulate matter formation in the atmosphere. So the secondary products and the primary emissions have very strong impact on human health. As I shown here, it impacts many parts and many organs of the human body. And they also have significant implications for ecosystem health. This I show ozone bleaching of healthy leaves and climate change, because we know that the particulate matter has a strong climate cooling effect, while CO2 and ozone are climate warming agents. Here is another climate ecosystem health impact from the reactive nitrogen and reactive carbon chemistry in the atmosphere. So here I show the basic reactive nitrogen cycling and their oxidation to nitric acid and deposition onto the terrestrial system. It could induce significant eutrophication and acid rain. And these impacts, climate impacts and ecosystem impacts, have feedbacks on atmospheric chemistry as well. So now I'll turn to my focus, HONO. As we know, HONO is the primary hydroxy radical source in the atmosphere. And it's important among the major oxidants, including ozone, formaldehyde, and itself. And we know it produces hydroxy radicals through photolysis in the wavelength range from 300 to 400 nanometers. And it is predominant hydroxy radical source in the early morning, but it's also important throughout the day. On the figure right, on the right side, I show an example of the hydroxy radical contribution from HONO compared to ozone throughout the day. As we can see, y-axis is the OH production and x-axis is the time series. We can see in the red, HONO production of hydroxy radical is important throughout the day. So we know it's important. And here I would like to show what is known well and what is not known well about HONO sources in the chemistry. So what's known well for HONO in the daytime is its photolysis and in the gas phase, and it's the gas phase formation of HONO from the backward reaction between NO and OH. And during the night, it's been studied a lot that heterogeneous reaction of NO2 on water, on surface water, can produce a significant amount of HONO. And recently, there are also several other important pathways that are proposed and verified in the lab about the heterogeneous formation of HONO during the day. First is photolysis of nitric acid and particulate nitrate on a variety of surfaces. And second is the photo-enhanced NO2 conversion on a variety of surfaces, for example, soot organic surfaces like humic acid and iron oxides. And in addition to those secondary pathways, there are direct emissions sources, including vehicular emissions, soil emissions, and biomass burning emissions. And these all have large uncertainties, especially the secondary, heterogeneous secondary pathways. For example, the nitric acid photolysis, in terms of its photolysis rate, there exist 3 or 4 orders of magnitude of uncertainty. And for NO2 conversion, the optic coefficient of NO2 can range easily up to 2 orders of magnitude on different surfaces. And also, there are a lot of uncertain sinks of HONO on different variety of surfaces. It can also range up to 2 to 3 orders of magnitude. So this presents a challenge for the current model to accurately predict observed HONO. So here's an example I show that from Zadar et al. The model prediction underestimated observed HONO by more than 40%. And there may be other secondary pathways that we are still unaware of. So currently in model simulation, HONO chemistry that I listed in previous slides are not well represented in the model. Here I show both global and regional scale modeling by including HONO to some extent and see their impact on oxidants like OH and ozone. On the left-hand side is a study that forced the HONO to ratio to 0.02 compared to no HONO forcing. And we can see the impact on the upper panel. We see the different OH enhancement in different regions, and the major enhancement OH are in the continental Asia, Europe, and North America. And a similar trend can be seen on enhancement of ozone. This is for global scale modeling with the impact from HONO forcing. On regional scale, I got another example which was conducted in Southeast China. We can see that the introduction. So in this study, they took a little bit more aggressive approach by including 6 different pathways and sources of HONO to match the observed HONO level. And by doing that, they saw very enhanced HONO ozone concentration resulting from the HONO sources and pathways by up to 12 ppb. That's very significant compared to the national standard. However, one of the big issue is that from that study, we can see the contribution from each sources and pathways are highly uncertain. It's very easily to get up to plus minus 40% of uncertainty associated with these pathways. So how can we track HONO sources, chemistry, and sinks? So traditionally, and there are very great methods for concentration measurements with very high time resolution, such as SIMS, DOAS, LOPAP. These concentration measurements give us very valuable information in terms of its time series and the concentration levels during pollution and non-pollution day. However, they are not completely sufficient for deciphering secondary pathways and relative contributions from each sources and pathways to HONO budget. Foremost is because the ratio of HONO to NOx is normally used as an indicator for sources, but it's not completely distinguishable among different sources like soil emissions and the vehicle emissions. There are big of overlap, and the soil emissions and the biomass burning emissions, there is some sort of overlap. And it's even complicated by secondary pathway. So at Brown University, in collaboration with Dr. Meredith Hastings, I use stable isotopes to track the HONO fate. So first, we use nitrogen isotopes, and by denotion, nitrogen isotope we use delta. It's basically the ratio between the isotope ratio in the sample to the isotope ratio in the standard. For nitrogen, the standard is air. And for oxygen, similarly, we use delta 18O. It's the standard here for oxygen is Vienna standard mean ocean water. And nitrogen is used to track the sources as fingerprints, and it holds potential for tracking the secondary pathway through reactive nitrogen cycling. And oxygen is a strong indicator. Oxygen isotopes is a strong indicator for the oxidation pathways, for example, peroxide versus ozone. And similar, in addition, there's another very significant indicator for oxygen isotopes, which is cap delta 17O, which is a difference between the delta 17O and half of delta 18O. So these are the major tools that we use to track the HONO sources and chemistry. So here's a little bit a discussion of why delta 15N of reactive nitrogen allows for tracking sources and cycling. For sources, because the formation pathways and the source material have different delta 15N, and the formation of NOx and HONO pathways from different sources are different. That results in different fractionation processes. For example, in vehicular emissions, the thermal combustion is major reaction pathways. By contrast, for soil emissions, the NOx and HONO are mainly formed from microbial processes in the presence of enzyme catalysis. And for biomass burning, the source materials is vegetation nitrogen instead of air nitrogen. So the formation process of reactive nitrogen is compared to vehicle emission is low temperature combustion. So these source difference and the reaction pathway difference makes the unique fingerprints of delta 15N of NOx and HONO. A little bit more discussion on delta 18O of reactive nitrogen species. Here I show a relationship plot between delta 17O and delta 18O. As you can see, for the major oxidants in the atmosphere, like hydroxy radicals, oxygen molecules, and peroxy radicals, as well as water, they all fall on this line, which is called terrestrial fractionation line. And in addition, their delta 17O and delta 18O is relatively small compared to ozone. Here, ozone presents the biggest anomaly in terms of oxygen isotopes, not only because it deviates from the relationship, it's deviates from the fractionation line, but also it has very elevated delta 17O and delta 18O. So any species involving the ozone contribution through the atmospheric reaction would present some sort of anomaly, like elevated delta 17O, delta 18O, as well as deviation from the fractionation line. For example, oxidation from NO to NO2, as we can see, the basic knowledge is that the branching between peroxide versus ozone oxidation of NO2 leads to the NO2. So the different branching between these two pathways would present different deviation from the fractionation line and different delta 17O and delta 18O values. Furthermore, the further oxidation of NO2, for example, to nitric acid and HONO would also, and reduce of NO2 to HONO would also contain some sort of the delta 18O and delta 17O signal from ozone. So that's the background. Next, I will talk about the method that I developed at Brown to track HONO isotopic composition and its field applications, and then ongoing work including both laboratory application and field application, other field application. So here's the method. This is the first method that I developed for capturing HONO for isotopic analysis. the basic concept is very simple. So we use two annular denuders to collect the HONO and correct the HONO from other NOY interference. Before the denuders, we put non-absorbed filter to remove nitric acid and particulate filter to filter out particulate nitrate. So after collection, the denuder coating are extracted by ultra pure water in the solution phase in the form of nitrite. Then the nitrite will be introduced into a bacterial, which is called the denitrifier method. So this kind of bacterial converts nitrate and the nitrite to N2O without further conversion to N2 because it lacks that enzyme. So the N2O converted from nitrite will be introduced to isotope ratio mass spectrometry, which detects three M to Z values, ratios 44, 45, and 46, which give us the isotopic composition delta 15N and delta 18 of HONO. And our laboratory validation shows that the accuracy of this method is 0.6 per mil for delta 15 and 0.5 per mil for delta 18O. So with this method, I deploy the instrumentation to 3 different fieldworks by tracking the fingerprints of these direct emission sources. So the first, I participate in fire lab studies and FireX AQ in the field later in 2019. So here is the laboratory controlled burning studies in 2016. So as many of you are definitely familiar with this, so we collect the biomass burning emissions by burning different vegetation in representative of Western US, and we collect them on the platform, which is 20 meters above the burning site. And then we measured the online concentration of HONO and NOx, and we collected the HONO and NOx and nitric acid and particulate nitrate for isotopic analysis offline. So here's some highlights of the results. So in order to validate our method for biomass burning, we first compare the denuder retrieved HONO concentration, which is a longer time integration compared with the high time resolution measurements, including mist chamber and chromatography and absorption spectroscopy and UV and FTIR, as well as SIMS. So there's a pretty good agreement between our annular denuder collected HONO and other high time resolution measured concentration. So the major goal for this comparison is that we want to make sure that the collected HONO are complete. And if it's not complete, the isotopic fractionation might happen, which would impact the accuracy of our isotopic quantification. And for isotopic results from the laboratory controlled burning, we first find that the delta 15N of HONO and NOx are both driven by delta 15N of biomass. And furthermore, by comparing the delta 15N HONO in y-axis and delta 15N of NOx in x-axis, we found a linear relationship, which shows that they are co-emitted and sort of reflect the formation mechanism during the biomass burning combustion processes. And the relationship reflects the dominant nitrogen flow at moderate temperature around 700 degrees C. So this relationship, please keep in mind, and later I will compare it with other sources like soil emissions. You will see very contrast relationship. And this will also this was also used for the field for interpret the field studies in FireX AQ to decipher the HONO formation mechanism. So the second application for source tracing by using my approach was vehicular derived HONO. So for this study, I conducted 3 parts. First part is the on-road highway mobile measurement, which is in collaboration with my colleague Wendell Waters. So we drove our custom-built mobile van northeastern corridor for 5 days and the track and collected the HONO samples and other reactive nitrogen species for isotopic analysis. And the second part was the highway roadside, which also represents the fresh emissions, like relatively fresh emissions of vehicles. And third part of the vehicular derived HONO is we measured urban ambient HONO at the Providence site near Brown University at 2 different periods. So here's one highlight from the vehicular derived HONO measurements, which is the mobile lab measurements. So we started from Boston, and we first take the eastern pass, which is I-95, down to almost Washington, D.C. And then we took the western pass here back to Boston, and we collected the HONO samples and measured both concentrations and isotopic compositions. So here's the delta 15N results. We see that the eastern pass is more negative, while the western pass, which is more warm color, is more positive. And the western pass is associated with the highest HONO concentration of up to 4 ppb. And this is very interesting results because we know from the vehicle fleet composition, we know that the western pass is more like a heavy truck roads, while the eastern pass is more like a light vehicle pass. So this is kind of reflect the vehicle fleet composition. And by comparing the on-road measurements with the highway roadside measurements, we found they're consistent with, which gives the delta 15N of HONO about 0.5 plus minus 2.2 per mil. So the third application and deployment of my HONO instruments, along with the NOx collector, is to measure the agricultural soil emitted HONO and NOx. This was part of Pennsylvania State University Sustainable Dairy Cropping System project. And this was done in collaboration with my former colleague, David Miller, in collaboration with USDA and Pennsylvania State University. So I call this a movable lab. So we purchased a small cart and secured our collection system and the NOx online measurements instrumentation on the small cart and drag it in the agricultural soil field and measure using a flux chamber shown here. And this is a more detailed diagram of flux chamber and the gas flow. We measured the different plots with different the soil management practice, like tillage, non-tillage, injected manure versus broadcast, and measured the variation of soil HONO and NOx emissions and their isotopic compositions. So here's the results highlight. I show here is, again, the delta 15N of HONO in y-axis in relative to delta 15N of NOx in x-axis. As we can see, delta 15N of HONO is much more positive than delta 15N of NOx, meaning 15N in NOx is more depleted. This reflects the pathways. It possibly reflects the microbial process in contrast with the abiotic process, because currently there is still debate whether soil NOx and HONO emissions are dominated by abiotic or biotic approach. So our results, I think it's it supports the biotic process because the more enriched delta 15N of HONO. So I don't have enough time to discuss why it is this, but I'm preparing a paper for this, but I'm happy to discuss afterwards. And by putting all the three source signatures together, I did this plot, delta 15 of HONO in y-axis versus the concentration of log concentration of HONO, gas HONO. Although the vehicle derived HONO is relatively fresh, it's not like pure fresh smoke, but it's still it could represent the source signature, especially for delta 15N. And its delta 18O might be different, but delta 15N is definitely representative. So as we can see that among the three sources, delta 15N of HONO in biomass burning presents the most positive values. And its concentration weighted average is 2.9 plus minus 4 per mil, while the vehicular derived HONO has a delta 15N of lying between in the middle, which is negative 0.5 plus minus 2.2 per mil, while the soil emitted HONO has the most negative delta 15N, which is negative 15 plus minus 9 per mil. And this is exciting results and give us confidence to further using this approach to decipher the HONO mechanism and budget. So we have the source signatures and the method, and here is an example of how we apply this approach to a specific system, which is biomass burning, to find evidence for primary and secondary HONO emissions. So this part was done by participation in FireXAQ and Weekend, FireXAQ in 2019 and Weekend in 2018, in two different mobile lab platform. So we mounted our instruments in the mobile lab in combination with a bunch of other online measurements in both gas phase and the particulate phase. So our major measurement was to collect the different reactive nitrogen species and bring them back to the lab for the isotopic analysis, including delta 15N, delta 18O, and cap delta 17O. And at the same time, we measured online concentration of HONO and NOx. And we drove the mobile lab to different smoke ages and during both day and night. So here's some picture of the mobile lab platform. So this was back in 2018 during weekend. We loaned the NOAA mobile lab and install our instruments. This is the reactive nitrogen collection system for Brown, and this is the online NOx measurements. This is HONO measurements by mist chamber and chromatography. And down here is the NOAA instruments for gas concentration measurements of CO2, water, CO, and methane. And we have different time resolution for the isotopic analysis depending on the concentration. So if the concentration is low, then we need to collect for longer time. And the major detection limit of this method was determined by our isotope ratio mass spectrometry and the bacterial method. And during 2018 weekend campaign, we focused one fire, which is called Rabbit Foot Fire in eastern Idaho here. And this is a fire. So here's some brief results for the concentration. Top panel is NOx, and middle panel is HONO, and bottom panel is NOx to HONO ratio. As we can see, the concentration of both NOx and HONO progress and increased as time goes by. And this is consistent with the fire progression because the Rabbit Foot Fire started around August 4th, and it peaks in late August. From the HONO to NOx ratio, as we can see, it's not very distinguishable among different colors. Oh, by the way, the different color means the different smoke conditions. Like YN is young smoke during nighttime, YD is young smoke during daytime, AN is age smoke during nighttime, and AD is age smoke during daytime. And this grouping was based on our delta 18O results, which I will talk about in a few minutes. And during 2019, this is the driving map of our mobile lab platform, and we investigate 5 different fires and across 5 different states, and we drove over 3,000 miles. And we got the best results and most of samples from William Flats fire in Washington and the NASCAR fire in Idaho. And they are very like big contrast, because William Flats fire, we expect it was a more of a flaming fire, and the NASCAR fire is more of a smoldering fire. So the emission patterns are different. And this is the pictures of our 2019 field campaign. On the top 2 picture, they're William Flats fire. And the bottom picture here is the NASCAR fire. During the NASCAR fire sampling, we get really close to the fire. This is a sample that we collect in the NASCAR fire for 30 minutes. For the filter, you can see how dark it is. That's me and the graduate students, researchers working with me during the field campaign. Okay, here's some of the highlights of results. So first, we use the delta 18O of HONO to estimate smoke age. Because smoke age is challenging to determine in both, especially in near grounds. And the current approach that scientists have used includes physical age based on distance, wind direction, and speed. But this is challenging in ground measurements because the variation of wind direction and speed is very dramatic. And also, the previously used smoke age determination is photochemical age. But this is inaccurate when source is far away. And recently, particulate matter to CO ratio was recently suggested as an estimate for smoke age by Bob Euclison's group. So here, this provides a very unique opportunity for us to track the smoke age by using delta 18O, because we have the laboratory results from Fire Lab in 2016, and those results, those samples have no photochemical processing. So we can be sure that although the delta 18O of that value are representative of fresh smoke. So by using by comparing our field results with the laboratory measured delta 18 of HONO, we grouped our samples into 4 different stages. The day and night are definitely grouped already because of the sampling time. The young versus aged are basically grouped by delta 18O. As we can see that the age, the nighttime, and age daytime derived the delta 18O of HONO are much elevated compared to the young smoke in daytime and nighttime, especially during the age daytime smoke, it can the delta 18O of HONO can reach up to 80 per mil, which is a strong indicator for ozone participation. By using this grouped results, we grouped our delta 15N into these 4 smoke stage, including here. Here I spell out the letter to the full name. Y is young, A is age, N is nighttime, and D is daytime. So first, let's look at young nighttime and young daytime samples in the delta 15N of HONO and delta 15 of NOx relationship plot. As we can see, this young smoke samples fall well within the laboratory prediction line, and they are more positive, which is consistent with our concentration weighted average of the delta 15N values from the laboratory results. And that's regime 1. And then regime 2 on the top left panel in orange, it shows the age daytime samples. And these samples shows shows 15N enrichment in HONO relative to NOx. And this relationship deviate from the laboratory prediction. And in regime 3 represents the age daytime derived HONO and NOx. As we can see, not only delta 15N is depleted in HONO in relative to NOx, but also the trend of these values deviate from the laboratory prediction. So these 3 distinct regime provides the indication of the secondary chemistry that impact the relationship. So here I list the key reactions that are important for these different regimes, and introduce the isotopic mass balance model to model the results, and also this modeling are in combination with the concentration results that basically shows the production of HONO from gas with OH plus NO is less than 15%, comparing its photolysis loss during the day. And here is the results from the modeling by combining isotopic composition measurements and the concentration measurements. So during the daytime aged smoke, we found that NO2 heterogeneous conversion dominates HONO production in addition to OH plus NO, as you can see from the relative contribution. And surprisingly, nitrate photolysis plays a less important role, which is in contrast with the airborne modeling study from Johan's group. So that at the same time, that's not quite surprising because on the ground level, the surface area is huge compared to the air. So the surface NO2 conversion suppress the nitrate photolysis, while during in the airborne measurement in the air, the surface is much less, and the NOx, the environment is more NOx limited, so the nitrate photolysis could dominate. However, our measurements here are conducted by a longer time integration, because our collection ranges from like 30 minutes to nearly 12 hours. So our results are like more represents the average contribution during those period, and we cannot rule out the nitrogen photolysis dominance when there is very thin smoke or background air. Yeah, so delta 18O, the second point here is delta 18O of HONO is used to quantify the branching ratio of NO oxidized by proxy versus ozone, and the values are shown here for age day and age night, and the figure is not shown here, but it's discussed in the paper because I have no time. And our delta 18O of HONO have also been used to constrain the HONO formation mechanisms during the nighttime to distinguish NO2 hydrolysis against the NO2 to HONO formation by the redox pair, like iron oxides and the humic acid. And this modeling certainly have some limitation. As I said, it cannot rule out the the nitrate photolysis dominance in the background air, that's one, and two, the longer integration time prevent us from doing that, and three, for the modeling, the isotopic fractionation factors have never been measured, but we used our the best understanding of theory to predict the fractionation factor associated with all the HONO formation and loss processes. And the model is the isotopic mass balance model is also simplified because we removed all the minor reactions that have very small impact on the isotopic change of delta 15N. I'm nearing the end of my talk, so I would like to, before I go into further research, I would like to conclude here. So our current progress shows that delta 15N of HONO can be distinguished among direct emission sources, including vehicle, soil, and biomass burning emissions. And we use our delta 15N measurements and concentration measurements and our isotopic mass balance model, and we for the first time determined the HONO budget and its apportionment via stable isotopes. And this certainly provide us a future path to further explore the HONO budget in this direction by completing the HONO mechanism via more advanced 0D photochemical box modeling. And delta 18O was used to quantify the branching ratio of NO to NO2 oxidation and HONO formation from NO2 and nitrate photolysis. And also it provides constraints on nighttime NO2 to HONO formation pathways. And in terms of the modeling results that I showed before, I showed that from the biomass burning studies, surface NO2 conversion accounts for 85 to 95% of all HONO production. But our results, modeling results, cannot distinguish what kind of surface reactions. As we know, there are varieties of NO2 to HONO conversion on different surfaces in both dark and light condition. So that leads to my current ongoing project. This is funded by NSF, which is a laboratory investigation of isotopic characterization of secondary HONO production pathways. So here, in order to do this, I built up a flow tube shown here. The orange part is the flow tube insert that can be coated with different materials that are representative of atmospheric surfaces. For example, the coating can be any like HONO related surface like titanium dioxide, iron oxides, quinone, soot, ice, as well as the soil surfaces, which I have done recently. So basically we introduce the reacting gas, either HONO or NO2, through the injector, and injecting the buffer gas like nitrogen from the side arm to control the concentration and residence time of the reacting gas. And we collect the HONO NO2 on the outlet, and while we have a bypass to do the online concentration measurement of HONO, NO, and NO2. And for the details of this research, I will have a poster. Sorry, this is 2021 for in about a week. It's the name is a method for isotopically characterizing heterogeneous HONO production pathways. So in that talk, I will discuss mainly the validation of the approach and the application of it to determine the fractionation factor of HONO uptake on soil surfaces and the soil surrogate surface like sodium carbonate and sodium bicarbonate and acid displacement reactions. And a second ongoing research is to apply the approach to more complicated environment like urban air, because urban air, in addition to mix the emissions like vehicular, industrial, and soil emissions, there are strong influences meteorology on reactive nitrogen cycling, and it has very strong implication for environmental justices. So one example is that the lake breeze impact on urban air quality that I recently participated in. So here is the basic scheme for land lake breeze. So during the night, land to lake breeze will bring all the fresh emissions in urban to the lake surface or the air above lake. And during the day, after the secondary, a lot of chemical processes in the early afternoon, the lake to land breeze will bring all the aged pollutants back to the land, which have strong impact on the ozone concentration as well as particulate matter. Detroit in Michigan is such a place that normally experience high ozone levels in early summer. So during this summer in 2021, in collaboration with my colleague from Wayne State University, Michigan Eagle, and State University of New York, and we conducted this 1 month campaign by doing stationary measurements of online concentration of the reactive nitrogen and offline isotopic collections. So we determined a time series of the concentration at 2 sites. One is the urban site, which has a lot of fresh emissions, and the other site is downwind rural site northeast of Detroit. In addition to the concentration, we determined the isotopic compositions of HONO, NO2, nitric acid, particulate nitrate. And there are also other simultaneous measurements of concentration, including ozone, particulate matter, and carbonyl compounds, as well as other like meteorological parameters. So that's the first stage. The second stage is by incorporating our field measured results into a 0D photochemical box model. We aim to develop an up-to-date reactive nitrogen mechanism, especially including the HONO mechanisms to improve the accuracy of the HONO representation in the 0D box model and chemical transport model. And the final stage, which is not happening now, but will be next year, is to include the up-to-date mechanism to chemical transport model to quantify the role of HONO in urban on regional ozone and secondary aerosol budgets. Oh, by the way, this is the grant that I just got this early this year, and luckily we have just 1 month, but enough time to get ready for the field campaign. And I will discuss the results in the upcoming AMS presentation. Yeah, the title is Probing the Fate and Transport of NOx and HONO during Moose campaign. So another ongoing research is also my biggest interest is indoor air quality and HONO production potential on indoor surfaces. And from the recent home campaign, that we know that the major HONO concentration is very significant and high in indoor environment. During the cooking stage, the HONO can reach up to 100 ppb. And during non-cooking stage, the HONO, the steady state HONO concentration is always 2 to 3 or 4 ppb. And however, the mechanisms and pathways in indoor HONO are poorly known. And so far we know that indoor has a large surface reservoir for HONO deposition, which conserve HONO as nitrite. And during the non-cooking period, but cleaning period, when you apply acetic acid, the HONO will be released, which creates the HONO peak in indoor by up to 10 ppb. However, this is not mass balanced. And it's unknown that since the indoor surface is so huge, it's unknown that the surface NO2 to HONO production, how is it important in relative to the surface reservoir acid displacement reactions in terms of maintaining the 2 to 3 ppb of HONO in indoor. So to pursue this question, I just recently started by introducing a lot of indoor related materials into my flow tube to measure like the uptake coefficient versus the reaction rate and the isotopic compositions to get a full understanding of all possible indoor HONO production and loss pathways. And this is a good point, I think, that I can collaborate with the NCAR, the ACOM scientists in terms of ranging from the chamber experiment to field measurements. So if you have any like upcoming indoor field measurements, don't hesitate to let me know, and I'm happy to participate. Yeah, with that said, I would like to acknowledge a lot of great scientists in Brown University, in Penn State, in USDA, and NOAA, NASA, Aerodyne Research, in Cooperate, University of New Hampshire, York University, US EPA, and Environment Canada, Wayne State University, and State University of New York, as well as my Chinese, my collaborators in China, which was for the Arctic and Antarctic snow nitrate isotopic composition campaign, which I didn't discuss in this talk. Yeah, so with that said, I would like to thank you for your attention, and I'm happy to answer any questions and discussions.
Thank you, Jiajue, for a very interesting talk. Yeah, it's really cool how you could you can span from indoor to outdoors, and you could do some interesting source apportionment to some extent. I might have missed it, but could you go over again how you go from the scatter plots that you show that are very clear between soil sources to traffic to wood combustion to quantifying how much HONO is produced from each source?
Oh, you mean this plot?
How did you go from the scatter plot to the pie chart? I guess that's the maybe more direct way to ask it.
It's not directly related. Like I didn't go directly from this source plot to the pie chart. The pie chart is only for daytime aged smoke secondary production. And I forgot to mention that the biomass burning field study, because we conducted measurement in very remote area. So the biomass burning study provided a unique opportunity for just the study the biomass burning emissions directly emitted from the source, and then after a secondary processing and reach our site. So that's only for biomass burning.
Okay. So then my question is, can you how do you go from your scatter plot to a source apportionment kind of thing? Because it seems like you could have all the information potentially, if you get an air mass that has sources coming from traffic, biomass, and soil, is there a way to disentangle that information from the measurements you've done?
Yeah, that's what we are doing now, like the Moose campaign project. So we have all the source information and secondary production fractionation factors that we measured in the lab. So those two are the input. And then we have the field observations. And we use we use these information we put them into a box model, 0D box model. For example, the delta 15N or delta 18O is just the ratio. So you can derive, for example, your HONO concentration, 14N HONO concentration is like 2 ppb, and then if your delta 15N HONO is like a value, then you can multiply a factor to that regular HONO, then that gives you the 15N HONO. So that are all kinds of the input. So you basically you duplicate for the 0D box model, you duplicate every reaction by introducing 15N. So it's just a 14N HONO and 15N HONO. So use that to reproduce the field observations to do the source apportionment. Yeah.
Okay, let's see if we have some questions from the people watching in streaming. Let me see. Oh, here we go. For the delta 15 HONO, nitrogen HONO, from the sources, end of part 2, do you know what is the dominant source of the scatter in the delta 15 nitrogen data?
Yeah. For biomass burning, the scatter, like as you can see, the delta 15 of HONO ranges from -5 to +7 per mil, and it's mainly determined by the variation of vegetation type and the combustion variability and combustion state. Like, yeah, and because some yeah, like for example, the water content of the vegetation could change the combustion temperature, right? That's one. And two, and different biomass materials have different nitrogen compound like composition. That's for biomass burning. For soil emissions presents the largest variation of delta 15N, but overall it's more negative. And it's the large variation is consistent with delta 15N of NOx. So I think because those are not measured within just one plot, so it's measured for different plots, including different soil management, including injection manure, broadcast manure, yeah, and in different days. So that results in the variation. And the smallest variation comes from the traffic measurements, because for that, we measured the mixed plume, right, emitted from the vehicles in the highway. So those are more like fleet dominant environment. I hope that answered the question.
Yeah, I hope so too. Okay, we have a couple of more questions. Do we have a need to account for fractionation during the bacterial digestion of your samples during the analysis?
Yeah, the isotopic analysis has account for all the fractionation during those. That's why we use we use 3 standard materials, nitrate material and nitrite materials to do the correction. We have a complete correction pathways. Yeah.
Next question. Could you comment on the pan interference in your NOx sampling method?
Yeah, sure. That's the comment that we received a lot from by publishing our ACP paper. I would say I didn't introduce the NOx, so it's a long story. I didn't introduce the NOx collection method here, but it's basically it used permanganate solution to collect the NOx, to oxidize it to nitrate and digest nitrate with bacteria for isotopic analysis. We don't have direct evidence for pan interference because we don't have the concentration measurement. So that's unfortunate. So we wish we would have, but we don't. So, but the only direct evidence is from our isotopic delta 15N of NOx. So based on the isotopic, so there for the isotopic effect, isotope effect, there are 2 different isotope effects. One is kinetic isotope effect. The other is equilibrium isotope effect. For reactive nitrogen with longer lifetime, for example, pan and NOx, which have like long enough time to do the isotopic exchange. So we expect that from previous theoretical calculation that PAN would have at least 20 more per mil delta 15N than NOx. So when if PAN is important to as interference to NOx, then the delta 15N of NOx in the aged smoke would be much elevated compared to our fresh smoke. But what we observed is the opposite. The delta 15N of the so-called NOx delta 15N is more negative. Yes, so this is a really great point, and it's always in our mind. And for the new proposal, we propose to investigate this interference. Hopefully, we can get the grant to investigate that. Yeah.
Nice. Okay, let's see if there is another question. No, looks like we don't. So it's what time is it? 4:36 p.m. here in Colorado, and it's time to say goodbye. Thank you, Jiajue, but hold on because we're going to continue after we stop recording. And thank you, everybody from the streaming crowd for joining, and see you in 2022, January 10. We'll be back. Bye-bye.
Bye. Thank you.